by various cosmological measurements, that's to say, by studying how things have evolved and looking out what's out there in the sky, we can determine what type of matter is out there. It turns out that the kind of matter we see is only about 5% of the universe. That is to say, stuff made up of protons and neutrons, the kind of stuff we're made of, seems to be only about 5% of the energy. About another 25% seems to be something called dark matter, which is matter that's just like matter in the sense that it clumps together. If we look at galaxies, there's lots of dark matter. But it doesn't interact with light in the same way that the matter we know about does, which is why it's dark and why it's hard to see, where I mean literally see with light. So we know it's there because of the gravitational effects, and there's various ways we've seen those gravitational effects, but we don't yet know exactly what it is. In addition to that, more recently we became aware of the fact that most of the energy density in the universe consists of something that's become known as dark energy. So that is very different than dark matter. Dark energy is just energy that permeates the universe. It's not associated with any particular type of particle, any type of matter. It's just out there. So if there was nothing, no particles around, there could still be this kind of energy. And in addition to that, that energy doesn't clump and it doesn't dilute as the universe expands. So it's a very special type of energy that Einstein first thought could be around. It turned out it was there in the amount that Einstein thought, but there seems to be this amount, this residual dark energy that's left, that seems to dominate the energy density of the universe today. We have a pretty good idea of how the universe has evolved to today, and remarkably in the last however many years, we've really been able to test the evolution of the universe, the cosmology model we have in much greater detail than we have ever had before. So it's really made cosmology into a precision science in a way that it hadn't been earlier on in the century. We now have something which we call the Big Bang Theory. A Big Bang Theory is a little bit funny because it's called the Big Bang Theory, but the Big Bang is the one thing we don't know about it. What Big Bang Theory tells us is really how things evolved at late stages, how the universe, given some energy density, which could consist of matter, radiation, dark energy, given those energies, how is the universe evolving? What's happening? So the Big Bang Theory tells us how it evolves, and we have really nice experimental confirmation. We've seen that the universe is expanding. We've seen the Hubble expansion. We've seen the relic radiation left over from the early time. In the beginning, it was all hot and dense, but as the universe expanded, the radiation has cooled down significantly. So now we see this 3-degree microwave background in the sky. And in addition to that, we even have detailed predictions for the abundance of various nuclei, which is very much connected with what happened as the universe cooled. So they're really good tests of the Big Bang Theory and this theory of expansion. The thing is, it doesn't tell us about the early stages. And in particular, there were some mysterious features when we looked at this background radiation, and I'm using we very loosely. Other people went and looked out at the sky. And it was seen that radiation was very uniform and it was homogeneous and isotropic. It looked the same in all different directions in the sky to a very, very high degree of precision, like 1 out of 10,000, with very small temperature deviations as you looked out in the sky, which was very surprising because there were pieces of the sky that didn't even have enough time, according to the standard Big Bang Theory, to talk to each other. They're so far away that light could not travel between them in enough time. So somehow all these different regions of the sky had to have originated in some common place. And the theory of cosmological inflation combined together with the Big Bang Theory seems to be what really works. So for cosmological inflation, the idea is that early on there was actually an exponential expansion in the universe, driven actually by something like dark energy, except in a much greater energy density. And it drove this exponential expansion of the universe. Actually, later on in our evolution, we will also have an exponential expansion, but it'll be a much slower exponential expansion. But early on, there was this very rapid phase of exponential expansion where the universe kept doubling in size. And during that time, the universe grew an enormous amount. And then after that stopped, then that whatever it is that drove the expansion might have decayed, but somehow the stuff that becomes our matter got created. So in some sense, that is really the beginning that we can trace. The fact that there was some expansion, some inflationary stage where it exponentially expanded, and then afterward the sort of more conventional Big Bang Theory takes over. And what's really remarkable is that there is sort of an imprint of this stage of exponential expansion in the sky. If you look at detail at the cosmic microwave background, it's very much in agreement with the predictions of cosmological inflation. So it really does seem like this happened, and it explains some features. It explains the flatness of the universe, the fact that the universe doesn't. We can talk about the geometry of even the three-dimensional spatial universe, and it seems extremely flat. And again, that's because if you think of a balloon, if you blow it up enough, even though we know over a large scale it looks sort of round or spherical or oval, if you look at a small region, it looks very flat. So if you blow up a balloon enough, at any given region it looks flat. And the same way, maybe we blew up the universe enough that it looks large and flat. So inflation seems to explain many features of sort of the initial conditions of how things started before this Big Bang theory took over. Well, what really tells us about the ultimate fate of the universe is what we see today. What we see today seems to be this dark energy that dominates. And the other, as I said earlier, dark energy doesn't dilute as the universe expands. Radiation dilutes, matter dilutes. So although we know right now we have about 30% matter, if we include dark matter and our matter, that matter is, as the universe grows, that matter will become more and more dilute. And dark energy is going to just take over, at which point we will again have exponential expansion of the universe. At that point, we will cease to have matter creation in the way we do today, star formation the way we do. Eventually, we might have all the matter in black holes, but those black holes will radiate away. So we will ultimately have, if this is right, a large, essentially empty universe that will just keep growing. This is not going to be the dominant thing that affects any of our lives. This is a projection based on what we observe today of what would happen billions of years from now.